Hi, this is Dr. John Bergduff. In a previous video, we looked at some of the basic ideas of equations. What is meant by an equation? What's meant by a variable even? What's meant by a solution of an equation? And what's meant when we say we want to solve an equation? In this section, in this video, we're going to take a little bit of a look at how we actually go about solving some equations. We're going to be looking at linear equations. So to recall a couple things from our previous video, a linear equation is in one variable is an equation that can be written in the form ax plus b equals c. Operative word here is can, where x is a variable and a, b, and c represent real numbers. And we do make a distinction that the number a cannot be equal to 0. So an example of a linear equation, for example, would be 3x plus 5 equals 11. To solve an equation in one variable is to find its solutions. And the solutions are the numbers which, when we substitute for the variable, make the equation true. Now, in the previous video, we just sort of checked some things. We found a number, we plugged it in for x, and we see if it worked. That's obviously not a very efficient thing to do. It's going to turn out, for example, that the solution set of the equation that we have just written is the set containing 2, meaning that 2 is a solution. 2 is, in fact, the only solution. And we can check that by, substituting the 2 for the x Let's actually make that more color consistent here, just so we have the 2. There we go. And we're asking ourselves the question, is 3x plus 5, 3 times 2 plus 5 equal to 11? 3 times 2 is 6. 6 plus 5 is indeed 11. And that's just fine, but we really have to figure out, how do I know that it's 2 instead of just checking it? Well, if our equation is incredibly simple, it's easy to see what the solution is. If my equation were x equals 5 and I were going to ask, what do I replace the x with to make a true statement, that'd be pretty easy. The x would be 5. So the solution set of the equation would be the set containing the number 5. And actually, although that seems rather simplistic, it does give me an idea of a strategy, or a beginning of a strategy, for solving linear equations that are a little bit more complicated. Here's the idea. To solve an equation in one variable, isolate the variable. What that means is try to write an equivalent equation. That means one that has the same solutions as the original equation, of the form x equal a number. In other words, if I could take an equation like the one that I just saw, 3x plus 5 equal 11, and somehow transform it into an equation that looked like x equal 2, somehow magically, if I could make that happen, then it would be easy to see what the solution set is. Well, we can't really use magic, but there must be some principle that we could build on that would give me an idea. So this principle is stated in many different ways, and more precisely actually than this, but I like to think of solving equations as an idea of balance, and I call this the principle of balance. The principle of balance works like this. Generally, performing the same mathematical operation on both sides of an equation will leave its solutions unchanged, thus creating an equivalent equation. So I have a picture here of Lady Justice, and she's holding an old-timey scale. You don't see these anymore, really, except in books. But the way these scales work, notice that she's holding it at the top, and there's two pans hanging from the end of a crossbar. If you were to add something in one of these pans, that side of the balance would go down, and it would become unbalanced. The only way to rebalance it is if I add something of the same weight on the other side, and then that side would come back up and it would be balanced. Similarly, if you take away something from one side, it will become unbalanced unless you also take away the same amount on the other side. There we go. Had trouble doing that. So the principle of balance, performing the same mathematical operation on both sides of an equation, will leave its solution unchanged. Let's look at some simple examples of how we might do that. Suppose your equation is x plus 5 equals 9. Now that's, again, fairly simple, where you could probably just use your imagination and figure out what to substitute for x to make this true. But here is how we could use the principle of balance. I currently have x plus 5, going to leave myself a little space, equals 9. The principle of balance says that I could subtract a 5 from the left side. As long as I also subtract a 5 from the right side, the equation will remain balanced, and I should result in an equivalent equation, one with the same solution. If I do this, 5 minus 5 is 0, so the left side of the equation is nothing more than the x. Remember, that's kind of what we were hoping for. The right side of the equation, n minus 5, is 4. And my equation results in one of the form x equal a number. I've isolated the x, and that tells me that the solution set should be the set containing 4. I can check that very easily, actually in my head, but if I substitute the 4 where the x is, in the original equation, and I ask myself, is 4 plus 5 indeed equal to 9? Yes, it is. That checked just fine. Let's look at another one. A minus 7 equals 4. So the goal is that I want to isolate the variable. Notice I'm using a variable other than x, just for variety. That can be anything. I want to get the variable by itself. I have this principle of balance, which says that if I perform a mathematical operation on one side, I perform the same operation on the other side, the equation will be equivalent. That will leave the solution unchanged. So I might think about, well, what could I do to get rid of the negative 7 on the left? And sure enough, if I add a 7, that would get rid of the negative 7 on the left, and as long as I do exactly the same on the right side, I will keep the equation balanced. A minus 7 plus 7 is A. 4 plus 7 is 11. The solution set is 11. And we'll just check this one verbally. If you substitute the 11 for the A, 11 minus 7 really is 4. So that is the solution. Notice that what we are doing is we're basically doing opposite operations. When I had x plus 5 equal 9, I got rid of the 5 by subtracting. Subtracting is the opposite of adding. When I had a minus 7 equal 4, to get rid of the minus 7, I added. The opposite of subtracting is adding. So I use an opposite operation. What if I had 5x equal negative 15? Now going back to a previous video, when the 5 is written next to an x, the understood operation is multiplication. On the same line of what we've done in the other equations, the opposite operation of multiplication is division. And as long as I divide both sides by the same thing, the equation will be balanced. 5 divided by 5 is 1, which leaves me with an x. and negative 15 divided by 5 is negative 3, the solution set is negative 3. And I think we'll check this one more carefully. 5, substituting negative 3 for x, is that indeed equal to negative 15? Sure it is. That's the solution. Opposite operations. Now, just a quick caveat in here. The principle of balance basically works for all kinds of equations. Here, the operations we've been looking at are adding and subtracting, multiplying and dividing. You can square both sides. You can take the square root of both sides. There's just a lot of things that you could do. You could take a natural logarithm, whatever that is, of both sides. Now, in certain circumstances, there are some sort of variations or exceptions or special extra things to hang on to with this principle of balance. But the principle of balance, and we'll see all those as we study them, but the principle of balance remains the same basically for solving any type of equation. Let's look at one that's a little bit more involved. This one is more involved because I see that there is both a 3 multiplied by an x and a 5. If I were going to isolate the x, get the x by itself, I've got to get rid of both the 3 and the 5. Which one do I do first? Well, to give you something to think about here, I want to focus for a minute on the order of operations, and just in particular on the fact that in the order of operations, multiplication and division are done before addition and subtraction. Imagine that this equation, or at least the left side of the equation, is like building a house. The x is the foundation. And if you were going to build a house, you'd start by building the foundation. The 3 is the first operation you would do. Imagine that corresponds to building the walls of the house. And I'll put some windows in here just to make it more interesting, and a door maybe would be good. And then the 5 represents the roof. You put the roof on last. That's a really ugly house. But the basic bottom line is to build a house, you start with the foundation, you look at the operation closest to it and you do that first, and then you do the operation that's farther away or less important in the order of operations. If I wanted to tear down this house, would I take out the foundation first? Would I tear out the walls first? Probably what I would do is reverse what I did with the order of operations. I would take off the roof first, then I'd tear down the walls, and I'd be back to the foundation, which is the x, which is, after all, the thing that we're trying to solve for. So if you're trying to solve for 3x plus 5 equal 11, and you're wondering what should I do first, think of the order of operations in reverse. In order of operations, you would multiply first, then you would add. In solving the equation, you're taking the house down. You would do that in the reverse order. You get rid of the 5 first. So I would say 3x plus 5, and if I want to get rid of that 5, the 5 is currently added. The opposite operation is subtraction. So I'd subtract 5 from both sides. 5 minus 5 is 0, so I get 3x on the left. 11 minus 5 is 6 on the right. Now to get the x the rest of the way by itself, to completely isolate it, I would divide, getting rid of the last operation. 3 divided by 3 is 1. 6 divided by 3 is 2. X is equal to 2. I've managed to do that thing that I said I wanted to do of isolating the variable, getting an equation of the form x equal a number. That tells me that my solution set is the set containing 2. And I can go back and check this if I want to. At some point we may not check all of them. We may let that be optional. But this is saying if you replace the x by 2, Do you get a true statement? 3 times 2 is 6, plus 5 equal 11, and actually we checked that a little while ago. Let's try another one with the same idea. Notice here that we've got, we want to isolate the c, so we're using the variable c. C is multiplied by 2, and then we subtract a 7. If we want to tear the house down, we'll take the roof off first. That means doing the order of operations in reverse order. Order of operations would say multiply first and then subtract. If I want to solve for the c, though, I'll do that in the reverse order. I'll first get rid of the 7 that's subtracted. Using the idea of opposite operations, to get rid of a subtraction, I add. And 2c, the minus 7 plus 7 gives me 2c. Negative 4 plus 7, a negative plus a positive. The sign of the result is the sign of the number in larger absolute value. Negative 4 plus 7 is positive 3. To solve for c, c is currently multiplied by 2. To get rid of something multiplied, you divide. And I wanted to do one example where the answer turned out to be a fraction, just to avoid leaving you with the impression that answers are always whole numbers. My solution set here is 3/2. We better check that one. 2 times 3/2 minus 7. Is that equal to negative 4? 2 times 3/2. Think of the 2 as 2 over 1. The 2's then divide out. So you get 3 minus 7 equals negative 4, and 3 minus 7 is indeed negative 4. That is the solution set. Now our equations can get a great deal harder than these. Let me just do one more. What's unique about this equation is that there are variables on both sides of the equation. There's a 5x here and a 3x here. Still, it's an equation in one variable because the variable is the same. They're both x's. If it were an x on one side and a y on the other side, we'd call it an equation in two variables. But they are the same variable. Now, obviously, if our goal is something along the lines of x equal a number, it's not going to be a good thing to have x's on both sides of the equation. We need to get rid of the x's on one side or another. And that's actually not so hard to do. If I take my 5x minus 3 equals 3x plus 5, by that same principle of balance, it would be perfectly fine to subtract 3x from both sides. Whatever you do on the left, you do on the right. The 3x minus 3x would give me a 0. And on the left side, this is looking ahead a little bit, we're going to combine like terms. Because I have a 5x and a 3x, those are like terms. They have the same variable. I can combine them. If I have 5 of them and 3 of them, 5 of them minus 3 of them, think of it, if you like, as 5 apples minus 3 apples. If you have 5 apples and you take away 3 apples, you have 2 apples. 5x minus 3x is 2x. On the other side, the 3x minus 3x gives me a 0, so all that's left is the 5. And now we're back on more familiar ground, still using the principle of balance. Get rid of the subtraction first. So 2x minus 3, add a 3, opposite operation. 5 plus 3, whatever you do on one side, you do on the other to keep it balanced. 2x is equal to 8. And finally, to get rid of the 2, because it's multiplied, we'll divide both sides. And that gives me 2 divided by 2 gives me a 1. X is equal to 4. My solution set should therefore be the set containing 4. maybe we better check that one. 5, we believe the answer is 4. Let me look back at the equation here. 5 times 4 minus 3. Is that indeed equal to, and it was 3x plus 5, so 3 times 4 plus, was it 5? 5. Let's see if this is true. Order of operations, we're sort of putting this together now, so order of operations would say 5 times 4 is 20 minus 3. Is that equal to 3 times 4 is 12 plus 5. 20 minus 3 is equal to 17. 12 plus 5 is also equal to 17. That works. So indeed, the solution set was 4. Now in future videos, you'll see that we could make linear equations more complicated than these. But I think this will give you a good foundation. Hang on to the principle of balance as we go through this entire semester. You'll see it over and over again in different settings with some little variations here and there, but it is a fundamental idea for solving equations. Thank you very much.